Welcome to Data Science 1, Probability, Conditional Distributions. Things we're going to need to remember in order to get through this video: cumulative distribution function, probability density function, marginal probability density function, and conditional probability. Now, you have to go back way back when we talked about conditional probability, but I'm going to go over it again, so don't worry. Just as a reminder, the cumulative joint distribution is given by this. If we take the second partial, we're going to get the density function here for the joint probability distribution, or probability density, and then we can get the marginal probability densities by integrating out the variables that we don't want. All right, so back to conditional probability. So if I have two events, E and F, and I want to know the probability of E, given that we know an outcome of an F has occurred. So we can use our handy dandy formula here, which is probability of E given F, the vertical bar means given. It's the probability of E intersect F over the probability of F, provided the probability of F is not equal to 0. So we can use this in our discrete case. So here's our joint distribution we've been considering right here. And what we want to know is, suppose we want to know the probability of y equals 1 given x equals 1. So y equals 1 was female, given that x equals 1 was they got an A in the course. So if I were to look at this, I can look at this by saying, well, when is x equal to 1? And well, it's this area over here. When is y equal to 1? It's in this row across here. And the intersection of those two is that number right there. So it's the intersection of that number over the probability of 1, which is x equals 1, which is a marginal probability. Probability of x equals 1 is a marginal probability because we're going to add them together regardless of their gender. Well, I could rewrite this in terms of densities. F sub xy 1 over fx1. And I can calculate this, and I find that the probability is about 0.5257, so a little more than equally likely. So the key is this formula here, and I purposely put this in here because I wanted you to see how these probabilities relate to our distributions, and they do quite nicely. So this is the actual definition of a conditional probability density or distribution. It works the same in either continuous or discrete, so we're not going to make really that big of a difference. But it's the probability of the joint over the marginal. And here the marginal can't be equal to 0. And it sounds easy enough, but it's a little more involved because you don't get out a single distribution, right? Every time I change x, I'm going to get a different distribution. And that is what confuses people some. Okay, so let's just look here. So let's go back the other way here. So we can start with y equals to 0. Suppose I tell you with y equals 0, so you're given that information. What's the distribution of x? Well, I would have to go and get my marginals, which I did over here. They're pretty easy to get. Then I would take each one of these and divide it by the marginal. And that would give me this number here, 0.332, 0.289, 0.175, and so on. But if I change it to y equals 1, notice all the probabilities have changed. There's still a probability distribution, but all of these probabilities have changed because now I'm using the other row down here. So the idea here is that you have to be given the information. You just can't randomly pick what y is because you've been told y. You're trying to figure out what's the likelihood of an x value showing up. Okay, so this really does depend on the value of y that we pick, and I really want to stress that, and I'm going to stress that in the continuous case as well, because a lot of people think they're going to get one formula out or they're going to get one distribution out. No, you're going to get lots of them out. It depends on the value you pick. Okay, so let's go to the continuous case. This is a new example. I'm going to skip a lot of the math because this would be a good exercise for you to fill in some of the details. So here is what our marginals are. So you can go through, integrate those out, make sure you know how to come up with them. It's a good exercise. And here we have our marginal distributions. And if I'm interested in f of y given x, well, that's f of xy over f of x. And you would just plug things in, and this is where you end up. And you say, yay, I end up here. Well, okay, so let's keep going just a little bit. Suppose we want to find the probability that, using our marginal here, the probability that y is less than 1 given x equals 1? Well, it's a density, so I can do the integration just like before. 0 to 1, here x equals 1, so that means we plug in a 1 for every single x. Okay? So that gives us 1 over 14, 3y squared plus 3. That's what we're going to end up with. And if we go down, do all the integrations, we're going to come out here at 0.1607. This is the value we're going to end up with if we chose x equals to 1. Now, what happens if we choose x equal to 1.5? Well, if we choose x equal to 1.5, notice we go through and plug in 1.5 everywhere for x. And we this is our normalizing constant now. And then we end up here with 0.3253 is our probability. So the probability really depends on the value of x. Because if I look here, it almost doubles, really close to doubles the probability just by changing it from 1 to 1.5. So be aware of that. You can, these distributions really depend on x. You just don't change them or pick x willy-nilly or just out of your head. You need to be given that information in order for this to make sense. All right, so conditional probability distribution is defined by our formula here, and where we have a joint distribution and we have marginal distribution. The densities associated with them will allow us to better understand relationships between the variables, right? We saw that by just changing 1 to 1.5, the probability increased dramatically, almost doubled. So keep that in mind. We can look at that with relationships. And working with conditional densities can be a bit challenging, but can also provide great insight into properties of the distribution, which we'll talk about later, like this idea of memorylessness. So I don't think that's an actual word. But anyway, we'll worry about that later. So we're going to move on to the next video and see you there.